One of the major concerns in commercial application or in industry today is that a fundamental device, as simple as a heat exchanger, could have a significant impact on the release of CO2 into the environment. And this occurs because as a heat exchanger fouls, there's a reduced heat transfer from the processed water to the cooling water. And since heat exchangers are fundamental and the low-hanging fruit within any industrial process, this lack of heat transfer will overall affect the functionality of that heat exchanger. And then what occurs is the cooling water that is intended to remove heat from the process fluid. What occurs is that due to fouling configurations within the heat exchanger, there's a significant increase in pressure drop because of this impediment of water flow. Finally, what occurs is as water flows through the heat exchanger, whether it's a shell or tube or a plate or frame, the water is directed away from the heat exchange surfaces. And so again, you lose the capacity for heat exchange within the device, and that all has a financial and an emissions impact. So there have been many, many studies that have been done over the decades that show there's a direct correlation between fouling within a heat exchanger and the capacity for a production of extensive CO2 gases into the environment because of that. And there's a loss of heat transfer. There's a energy cost in that to compensate for this loss of heat transfer. Cooling water pumps will ratchet up, requiring increased energy to compensate for that lack of water flow. And all of this compounds the presentation of CO2 into the environment, and of course, the financial cost from excessive fuel burn. Besides the environmental aspect of it caused by carbon dioxide and other greenhouse gases, there's issues and concern of eliminating chemical waste from chemical or mechanical cleaning of the heat exchangers. There's limitations in cooling water use due to the effluents and temperatures that are involved in the discharge into fluid volumes. And then, of course, there's always a concern with the release of other gases besides carbon dioxide, such as nitrous and sulfur dioxide in the presentation within scrubbers. So there have been many, many, many studies that have been performed that show that because of fouling within heat exchangers, that there is a environmental penalty that gets paid. And a lot of this has been seen, again, anytime seawater is involved or any kind of cooler water is involved, that because the heat exchangers foul, there's a financial impact that is caused by this. And thus, not only is it from a financial aspect, but the labor involved, the cost in trying to capture these rogue gases, all of those impact the use of a heat exchanger significantly. So over the decades, it has been shown that merely applying air bubbles into a heat exchanger have the capacity to reduce foul formation within the heat exchanger. They also have been shown to have the ability to improve heat transfer through the creation of a wake zone within the heat exchanger itself, therefore moving heat away from the surfaces more into the water flow, and thus allowing for a greater heat transfer within the device. The problem has always been, though, that when you introduce a bubble comprised of either air or comprised of oxygen, that you have the potential of causing increased corrosion or the potential of forming a biofoul within the heat exchanger. Also, when you use bubbles that are of significant size, you always have a concern of impacting the water flow within the heat exchanger and the piping system. So therefore, you have to be cautious in how these air bubbles are presented. We developed a technology called vapor infusion. And what vapor infusion is we use specific chemical catalysts to create nanobubbles within the system. The beauty of this technology is that we do not have to impart it on a continuous basis. Rather, a few minutes every hour, we're able to inject into the cooling water flow these chemical treatments that induce the creation of nanobubbles through the formation of hydroxyl ions on the surfaces of microbubbles. These microbubbles will then shrink rapidly and form nanobubbles within that cooling water flow path. As these bubbles then move through the system, they will impact fouling surfaces such as biofoul or mineral foulants, and cause these foulants to become soluble in water, break away, and dissolve within the water fluid. The beauty of this technology is that because we're using nanobubbles and not micro or macro bubbles, we don't have an issue with creating back pressure due to air entrapment within the system. The other thing is that we're able to create nanobubbles that are excessively small, smaller than 50 nanometers, and very high densities. Because of Brownian motion, these nanobubbles fill in that flow path rather dramatically, therefore impacting all aspects of the interior piping system and all aspects of the heat exchanger itself. Again, because we only impart this on for a few minutes every half hour or so, we're not using excessive energy to create these nanobubbles. We merely are creating this nanobubble density that moves through the system, has impact on the fouling surfaces, and then the nanobubbles dissipate downstream and are extended into the cooling water source. The other thing that's most important about creating nanobubbles of this nature is that they have other characteristics. We will only use extremely low residues within the fluid. We use grams per month, for example, in many of the technologies and many of the applications that we use. And so as these bubbles move through the environment, the heat exchanger environment, what happens is they will impact with planktonic fouling species, bacteria, algae, things of that nature, and also will come in contact with potential mineral or sedimentary fouling species and interact with them in a way that they become both bio and electrostatically impactful. Because these bubbles create a very highly electronegative surface, they also have a very high zeta potential. This very high zeta potential is what will cause the inactivation of microbiological species and also cause fouling species from minerals to repel from the bubbles, therefore disrupting a potential foul formation. Because the chemical treatment is preserved within the nanobubble, and because the bubble surface is almost insoluble, we don't present to the fluid volume a high level of dissolved oxygen. This thus will prevent the potentially corrosive effect of dissolved oxygen and will prevent the formation of a biofoul within the solution. The other thing is that we don't affect the pH of the water flow itself. And as I mentioned, the chemical treatment remains preserved within the bubble itself. And because these bubbles are excessively small, they undergo that Brownian motion rather dramatically and will have the capacity to penetrate into fouling surfaces and cause them to be disrupted. As these bubbles move, though, across the surface, they do have a chemical surface that is comprised of whatever chemical treatment it is. And what they will do is impart some of the chemical treatment onto the surface itself. So, for example, when we use a vapor corrosion inhibitor, for example, we get a duality of effect in that not only do we prevent fouling, we also then impart a vapor corrosion inhibitor onto that surface. We use two primary chemical treatments. We use iodine, or we use a benzoate salt. And we use these based upon regulatory acceptance in the environment where the heat exchanger is, and typically what we're trying to achieve. In most aspects, if we're looking at a biological foulant, either one will do well. In a situation where we have extremely heavy mineral valence, what we tend to use is a vapor corrosion inhibitor, especially within a gas vapor scrubber system, where we want to have impact and possibly increase the effectiveness of the scrubber itself. But in either case, both of these chemical treatments will create nanobubbles rapidly within the cooling water path, do not present a high chemical residue within the fluid, and have, as I mentioned previously, very low chemical residues within the fluid and use very little in terms of chemical treatment itself. We've been fortunate to have 7 governmental studies with the U.S. government, with the USDA, U.S. Navy, and other aspects of the undersea warfare development in the U.S. Navy. And one of the things that they wanted to look at was, did we have the capacity to interact with biological contaminants within a fluid merely by imparting a chemical treatment as a bubble? As you can see from these charts, the chart to the left was a mere infusion of iodine vapor into a static fluid volume containing a very high log-6 count of pathogenic microbes. And as you can see, after only 90 seconds, there was a complete inactivation of all microbes within that fluid. 24 and 72 hours later, there was absolutely no rebound in the presence of these biological contaminants. The second chart, the one in orange, this was very important because we wanted to see if we were capable of creating an inactivation of biofilm in trained bacteria. And the same thing occurred. As you can see, that after a 90-second infusion, there was a complete inactivation of all microbes contained within a biofilm. Once again, 72 hours later, when we revisited the biofilm, there was no viable bacteria within the biofilm. Now, the interesting thing is that in commercial application, we will see a disruption and a reduction in biofilms merely by the presentation of these bubbles over a period of time. And I'll show you momentarily just how profound that biofilm destruction is. The thing is, in both of these applications, when they looked at the total iodine within that fluid volume, there was less than 50 parts per billion. So it wasn't an aqueous presentation of iodine that was inactivating the microbes. Instead, it was the interaction between the iodine bubble and the contaminant itself. Finally, the chart to the right, we wanted to see if there was an ongoing inactivation capacity to the bubbles that we create. And sure enough, with one infusion for 90 seconds and a new addition of a new inoculum every hour over a period of time, we saw that there was a significant disinfection quality up to about hour 4. Where without having to infuse again, we inactivated any newly introduced microbes. So we did a deep dive into what nanobubbles were, because originally we thought we were creating microbubbles. But we came to realize that since we were able to address all aspects of a cooling water system, if we were using microbubbles, they would rise and coalesce at the top of the pipe. And that was not happening. We saw that all aspects of the pipe itself, the interior surface of the pipe, were maintaining their cleanliness. And so that made no sense if microbubbles were being used. So in collaboration with UC Irvine in California, we came to understand that what we were creating was nanobubbles. So we did a deep dive into what capacity nanobubbles had in the reduction and prevention of valence, whether mineral or biological. And what you see here is just a small number of studies that have shown that introducing nanobubbles have the capacity to not only remediate, but also prevent valve formation within a system. When we did an investigation using a device called the NanoSite device, merely by infusing into a static fluid volume for a few minutes, we were able to create an extremely high density of extremely small nanobubbles merely by infusing this vapor into a cooling water path. And it was determined that because we were using a chemical treatment to create these nanobubbles, that the bubbles that were being created had an inherent attraction for negatively charged particles within the fluid. And these were causing a downward pressure onto the bubble itself that caused them to continually shrink to become the very small nanobubbles that we're able to achieve. Now, the interesting thing about this technology is that typically to create nanobubbles within a fluid environment takes a considerable amount of energy, a relatively long period of time, and more importantly, is not easily integratable into a system. By using this technology, we merely need an air source and the means by which to infuse the chemical treatment into the fluid volume itself. And so we're able to integrate this technology into robust cooling water systems with relative ease. The other thing that we found was that, again, when we looked at the fluid volume after infusion, once again, we saw that because of the relatively insoluble surface of these bubbles, we did not impart high chemical residues to the water. So from an environmental standpoint, we're able to achieve the benefits of nanobubbles without the creation of high chemical residues in the flow stream itself. The same thing held true whether we used either the vapor corrosion inhibitor or iodine. So both of those chemical treatments, along with others, we've been able to show that we can create nanobubbles that have sustainability. They will stay in solution for upwards of 3 or 4 days after infusion, and possibly longer. We just haven't looked at the total persistence time. So being able to use this technology in an environment whereby a recirculating system is in play, we'd be able to create a relatively high nanobubble presence within that fluid. So as I mentioned, we've been the recipient of a number of US studies, the first of which was with the US Navy. And what they wanted to do was compare within two similar heat exchangers on board a naval vessel, whether infusion would reduce the overall chemical treatment time or the time between cleanings of two heat exchangers on board this ship. And so what they did was they compared two shell and tube exchanges. One was to receive infusion, the other one was not. Their success criteria was that if we could increase the time between acid cleanings from 60 days to 90 days, that would be considered a success. The second thing is they wanted to be able to achieve this without an effluent in the seawater that was anywhere near 200 parts per billion, which at the time was what they were allowed to use for chlorine. And lastly, they wanted to see if the nanobubble presentation would have any effect on the metallic or gasket components within the system. Well, the total time allotted to the technology presentation was 270 days. Not only were we able to double the time in between, an increase of 50%, we actually went the entire trial time of 270 days without an increase in foul formation. In fact, when they did an acid wash before and after the end of the trial, they found that there was absolutely no increase in pressure, or rather no decrease in pressure before or after the acid wash, which indicated there was absolutely no foul formation whatsoever within the heat exchanger itself. So the technology completely remediated and then prevented foul formation. When they looked at the total effluent of iodine during really static mixing within the heat exchanger, there was only a rise of 35 parts per billion. So there was no transfer of iodine from the bubbles themselves to the effluent during static mixing. And lastly, when they looked at metallic ions within the effluent, there was no rise in metallic effluent ion effluent as well, indicating that the infusion protocol had no effect on metallic surfaces or gaskets within the heat exchanger system. One of the things that the Navy wanted to see was, first and foremost, was using these chemical treatments. Could we simply use an air bubble to achieve the same effect? When you look at the picture to the right, this compared a control to an air-only infusion to an iodine vapor infusion. And as you can see at the lower right hand, the lower elbow of all three flow streams, both the control and the air showed the formation of a significant biofoul, whereas the iodine did not show any fouling whatsoever. This was supported by flow pipes that contained metallic coupons, one of which was to receive infusion and the others which did not. And as you can see, the pictures to the left, after 45 days, there was a significant foul formation in those that did not receive infusion, whereas the flow streams receiving infusion had absolutely no foul whatsoever. And so once again, we were able to show that all aspects of the piping system that received infusion were clear of biofoul, not necessarily the case without infusion. So our very first client, which was 17 some odd years ago, had a significant fouling problem within a geothermal system. They would have to tear apart their exchanges literally every 6 weeks or so. By imparting vapor infusion into the system, after only 2 months, as you can see from the two pictures to the left, all the tuberculin formation in the upper flow space within the heat exchanger has been flattened out. But more importantly than that, the two pictures to the right, these are pictures of the stainless steel screens at the bottom of a recipient well. These are some 2,500 feet from where we've infused the vapor into the heat exchanger. As you can see, before infusion, there is a rather robust biofoul formation in and around the well screens and filling in the water flow at the bottom of the well itself. The picture to the right, though, shows after only 6 months that there's absolutely no biofoul whatsoever. The beauty of this is that there was no direct infusion into the well itself, and the nanobubbles that were presented to this foul were formed in the heat exchanger and then moved downstream to interact with the biofoul almost 2,500 feet away. And so, as I mentioned, in the 17 years that we've been treating this well, they have never needed to chemically clean or open up their heat exchanger ever again. Because of the application of this technology, we have a number of commercial applications around the world. And one of the areas that we've found a huge success is in offshore oil rigs, in the maintenance of their heat exchangers. This is one that is located off of the coast of Australia. And when they began, they had a problem with not only red mud, but also iron bacteria and iron formation. They have now been 6 years absolutely clean without having to tear apart their heat exchangers. Now, the interesting thing about this, having a significant heat exchanger profile, you would think that the infusion of chemical treatment would reflect in a residue within the effluent. The reality is that all heat exchangers functioning at the same time and being infused, when they look at the total effluent of chemical treatment, it's well under 100 parts per billion for this entire system during infusion. And again, keep in mind that when there is no infusion, there is no residue being imparted to the flow water itself. One of our great successes is, as I mentioned, in the remediation of existing foul. These are heat exchangers on board a cruise ship, the Norwegian Sun. They had a problem in that their heat exchangers had fouled, and their intention was to install these devices after mechanical cleaning when in dry dock. Unfortunately, they weren't able to get the ship in the dry dock, so they decided to install the system on already fouled exchanges. After a relatively short period of time, they began to notice that their heat exchangers were functioning as though they were clean. So after 26 months of infusion, they were able to get into dry dock and open up the exchangers. And what they found was that the exchanger plates were absolutely clean. The picture to the far right shows some shells, but that's merely because they don't have screens on their incoming water flow. But the plates from a sedimentary, mineral, or biological profile had absolutely no foul within the chevron flow spaces. And so they merely closed the exchanges up and went back into service. And now it's been almost 7 years and they've not had to open their exchangers and clean them. So as I mentioned previously, the technology is very, very simple to integrate, and we're able to integrate it into a lot of varied um, uh, industrial settings. It merely requires a compressed air source, a cartridge containing the chemical treatment, and the means by which to impart it into the flow stream. And so again, it's very easy to integrate. It doesn't require any modification or disruption of the system itself. It operates independently and does not require a shutdown of the system to operate. And what we have found is that typically they use only grams per month of the chemical treatment itself to impart these chemical treatments, because we don't need a very high level of the chemical treatment to create the nanobubble. So we reduce the amount of chemicals required to the lowest possible level so as to not impact the environment in any way. Now, from an oil and gas perspective, one of the areas that we'll begin to look at is in fracking, that we're able to create unique nanobubbles that are comprised of either ammonia or iodine, and they have the capacity to create unique characteristics in terms of fracking. Also, because we're able to create these relatively easy in a field environment, we're able to create these nanobubbles within a water entrapment and then present that as part of a fracking operation. And so the number of the benefits that are derived from vapor infusion are the functional aspect. You'll begin to see a vast improvement in the overall functionality of a heat exchanger. You'll see improved energy and fuel use, of course, but one of the key components of this is that unlike any other treatment, once a clean heat exchanger is brought online, they immediately begin the ebb and flow of foul, and they begin to reduce in functionality. With vapor infusion, that doesn't happen. With vapor infusion, you maintain the functionality and don't wait for a chronic condition to become an acute condition, requiring the heat exchanger to be torn down and clean. With vapor infusion, once the heat exchanger is clean, it maintains that cleanliness. In fact, in most situations, you will not see a reduction in functionality over a very long period of time. From an environmental standpoint, it'll help to reduce CO2 emissions by reducing the energy need by cooling water pumps. This will enhance facilities' net zero goals. There's, of course, a number of financial costs that are associated with fouling. And from a societal standpoint, being able to reduce an ESG score and having a positive marketing from being able to show that you're attempting to reduce overall environmental impact, that is all very important in terms of being able to help in reducing overall environmental impact. And so if anybody has any questions that you wish to ask me after the presentation is over, this is my contact information. Feel free to please reach out to me. I'll be happy to talk. I love talking about this stuff, as you can tell. And that's my presentation. And once again, thank you very much for having me.